Swayam Prabha. Digital India. Educated India.
Welcome to the next module. Online or sequential or recursive least square problems. I would like to first talk about the distinction between offline and online. So far we have assumed that the number m of observation is fixed and all the observations are known to us in advance. So when we say z is equal to h of x or z is equal to h of x, it is assumed I know all the z's. This treatment is also known as fixed sample or offline version of the problem. Is also called batch mode. Batch, B-A-T-C-H, batch mode. Why it's called batch mode? I'm taking a batch of data and trying to analyze it. The number of samples in the batch is fixed. It is offline because analysis starts after I complete the experiment. So I conduct the experiment, collect data, close the shop, come to the office, do the analysis. That's called batch mode analysis, offline analysis, or a fixed sample analysis. It is conceivable that the observations are not known all at one time, but they will be arriving in a sequence in time. In that case, it is prudent to get an optimal estimate based on m, the number of samples that you have on hand at that time. The number m of samples in this case keeps changing. In the previous case, we assumed the m samples are fixed in advance. So XLS m is the least square solution based on m samples where m varies from 1, 2, 3, 4 all the way up as long as the data keeps coming. So in such a case, I cannot wait until all the data arrives. I want to do my business. I want to be able to compute some optimal solution. So I would like to be able to keep solving sequentially the optimization problem, updating the solution as and when a new data comes in. Until such time I am going to use the old optimal solution. So this way you continue to be optimal conditioned on the number of samples you have. So I need to update XL of m to XL of m plus 1. Here m is the variable, m is the number of observations. So the estimate depends on the number of observation, and the number of observation keeps increasing. So here comes the challenge. When you have m observation, I know how to solve the least square estimate by m by solving using all the m observation as a batch. If the m plus 1th observation comes in, one way would be to redo the problem from starting from ground up using the batch mode on all the m plus 1 observation. But that will be little reflection revealed that's wasteful, because we have already solved the m sample problem. Now we want to solve m plus 1 sample problem. Prudence tells you that if you have a computed solution for the m sample problem, I should be able to reuse them to be able to update the solution when the m plus 1th observation come into the play. So that's what's called iterative, recursive, or sequential framework. So let x be unknown. Let z be Rm, be the vector observation that is given to you. Because I don't know all the observation, now I am going to attach a descriptor to the least square solution xl of m. That means the least square estimate conditioned on m observation. I have already solved the least square problem. This is H transpose, H inverse, H transpose Z. I am assuming again an overdetermined problem. Now, a new observation comes in Zm plus 1. So I already have Z1 to Z2 to Zm. Using this, I computed my XLS m. M plus 1 comes into play, Z of m plus 1 come into play. I would like to be able to compute XLS m plus 1. The whole idea here is that how do I relate xm plus 1 to xm? How do I relate the least square solution for the new problem to the least square solution for the old problem? So the goal is to find the new solution as a function of the old solution without having to redo the whole problem from ground up. So I already have this. This is the new data I get. How do I combine these two to get this? That means I have invested money in computing XL of m. I don't want to waste it. I want to build on my current knowledge by protecting all the investment I have made in computing the old solution. So what is the incremental computation I need to do to be able to update the solution is what we are after. Again, we are talking about model building. We are talking about estimation. We are talking about estimation within the context of regression problem, least square regression problem, online least square regression problem. So I am going to now start with a sequential formulation. Originally I had z is equal to h of x. Now I am having zm plus 1. Zm plus 1 is given by the last row of h, new h with x. I am going to call the last row of new h is h transpose m plus 1. So what is h transpose? So this n, this now becomes m plus 1. Up to this was m. So originally mn, this is m plus 1 n. N doesn't change, only m changes. So each time a new observation comes, I am going to add a row to h. So h m plus 1 is a vector in Rn, is a column vector. The transpose of the column vector is the row. That's a n vector. So I am going to partition after the m plus 1 observations arrive on the z. So I had originally z and a z plus 1 comes in. So this is the situation where I have already computed XLS based on m observation. A new observation comes in, the new setup. So h's are mn, hm plus 1 is rn, hm plus 1 is the new row added to h to account for the new observation. So I have to solve the new least square problem. So how do I solve the new least square problem? I am going to take a recursive view of the residual. So this is the old residual z minus h of x. The new component of the residual is z m plus 1 minus hm plus 1 transpose x, and that is given by these matrix relations. And this is Rm of x. Please understand z minus h of x is Rm of x. That is the residual from m observation. So the residual from m plus 1 observation is a vector whose first m components are Rm, and the new component, the m plus 1 component, is given by Zm minus the inner product of the m plus 1th row with x. So this is the new residual vector for m plus 1 observation. Rm of x is the residual for the old observation, or the batch mode using m observation. Recall, XL of m minimizes Rm of x. or m, conditioning, m number of observation. Now, knowing xl of m, I would like to be able to find xl m plus 1 that minimizes rm plus 1 x squared. So, this minimizes this, we already know. Now, this is the new guy in the block. This new guy in the block is the old guy plus something more. This something more is going to affect my least square solution. So, I would like to be able to compute the increment to the least square solution resulting from the new observation brings to the table. So, what is the objective function for the m plus 1 observation? That is simply the square of the sum of the square of the residuals. That is the norm of the vector. But this vector is given by Rm and this component. So, what is the norm? It is the norm of the Rm, the square of the norm of Rm plus the inner product of the last component. I hope you should be able to do that very easily. So, the norm square of that is the square of the norm of that plus the square of the norm of the following. That simply comes from the definition of the square of the norm. We are taking the Euclidean norm. The entire least square analysis is built around the 2 norm to start with. You may ask a question, is there a least square based on 1 norm? Is there a least square based on P norm, infinity norm? Yes. They are more difficult problems. We will talk about it later. Therefore, minimizing this equivalent to minimizing this when substituting the form of Rm plus 1 gives that. And this is equal to f of m. Therefore, I have a recursive formula. The sum of the square residual with the m plus 1 observation is the sum of the square of the residual for m observation plus an increment. That's beautiful. That's beautiful. Please understand, x doesn't change. Only the estimate of x changes. X is the unknown. So, this additive recursive relation for the square of the residual is quite basic and brings out clearly the contribution due to the new observation. So, this is the contribution due to the new observation. This is the contribution collectively due to all the m observation. I am able to separate the impact of old observation of the new observation. This separability, this additive separability is key to further analysis. This additive recursive structure. Why this is recursive? The residual with the m plus 1 observation is based on m observation plus an increment plus a correction. So, what do I now want? I want an x that minimizes. So, here is a function of x, here is a function of x. I want to be able to minimize the sum. The minimization of the sum, the one that minimizes it, x least square m plus 1, is what I am seeking. So, what do? We have followed this path now a million times. You concoct a cost function, you compute the gradient, you compute the Hessian. In the minimization problem, guarantee the Hessian is positive definite. You solve the equation for the gradient. So, here I am going to follow the same track. So, the gradient of the sum is the sum of the gradients. So, the gradient of f of m plus 1 is the gradient with respect to f of m plus an incremental term. I hope you are all with me now. But recall, the gradient for the m valued problem, we already know the solution. So, if I add these two and equate the equation, so substitute 6 and 5, equate phi to 0, we get a set of normal equations, new set of normal equation. What is the normal equation? H transpose H plus Hm transpose Hm plus 1 times Hm transpose. Now, please remember, this is the row vector. I am sorry, this is the column vector, this is the row vector. So, this is the matrix, this is the outer product matrix, is the outer product update, the right hand side is this. So how can I write this optimal solution? The optimal solution XL of n plus 1 is equal to the inverse of this update plus that. We already know H transpose H is SPD. So this is invertible. Now we are adding a rank 1 perturbation to that. We are talking about the inverse of a matrix with a rank 1 perturbation. You remember Sherman-Morrison-Woodbury formula? The very first formula Sherman discovered is exactly computing the inverse of this kinds of updates. So please remember, in principle I have solved the problem right now in 8. So what is involved? What is involved is to be able to compute the inverse of this rank 1 update. The rank 1 update can be obtained by Sherman-Morrison-Woodbury formula, which we have done earlier. Now please understand, we have fallen back on this formula a couple of times. This is the second time we are doing it. So matrix identities are very fundamental to doing model building, model analysis, estimations. Matrix theory is so rich, so powerful. It feeds into the estimation problem at every step of the way. So we have expressed the Morrison-Woodbury formula in terms of P and HH transpose. So setting H transpose H is P and HM plus 1 is H. For simplicity in the notation, assuming H is a full rank, H transpose H is SPD. This is the outer product matrix of rank 1. The inverse of P plus H transpose, this is exactly the matrix that we have gotten here. We call it P, we call it H transpose. We are dropping all the subscripts, not to be bothered in notation. So the inverse of this is related to P through the Sherman-Morrison-Woodbury formula, which you already know when we dealt with the modular matrices. So this inverse is now explicitly given by this. Please understand, this is the matrix. This is the quadratic function, so the denominator is a constant. This is the matrix, this is the matrix, that's the matrix. So the numerator involves 3 matrices, the denominator involves a constant. So by setting alpha is equal to H transpose P inverse H, I can express this as P inverse H alpha inverse H transpose P1. This is a fancy way of rewriting the same thing by hiding all the constants under alpha, so that I don't have to keep writing too many things. I can hide the details in the notation. So going back, so what is this? The new estimate is equal to the inverse times that. I already know the inverse of this using formula 9. So computing the formula 9 in 8, I am going to get the equation 10. So the new estimate is equal to the inverse times that. This inverse has been calculated in 9. Using that 9 in 10, I am going to substitute from 9, which is the formula for this. Yes, I can do it very easily in here, but I would like you to check each of these calculations. Please remember the Chinese proverb. You hear, you forget. You read, you remember. You do, you understand. So you have to do it. Don't believe me, check me out. And that's the best way to be able to understand it. So if I substitute this, this is in here. Now I multiply everything, simplify. I understand H transpose, H inverse, H transpose E is XLM. So this can be now rewritten as the new estimate is equal to the old estimate plus corrections. The correction term can be written very beautifully by simplifying the structure. So to simplify this, I am going to take the terms in here on the right hand side, the correction term in 12. So I am taking this term, I'm trying to simplify this, it is equal to this. Substituting 13 in 20 in 12, you can readily see my new estimate is equal to the old estimate. This is a matrix times, so look at that, this is a matrix times a vector times a constant. So this is a vector, Zm is a constant, H transpose XLM, this is again a scalar, so this is a scalar, this is a vector, this is a vector, this is a vector. So what is this called? This is called the innovation or the correction term, the new information from the new observation. So what does this say? The new estimate is equal to the old estimate plus a correction term. So all I need to do is to be able to compute the correction term to be able to add to that. That's the beauty of recursive sequential estimation. Sequential estimation. So we have algorithm depending on what the kind of problems you have. Now I am going to rewrite this. I am going to rewrite the structure. So I am going to introduce the new term Hm inverse is H transpose H. K inverse is Hm plus this. Using Sherman-Morrison-Woodbury formula, you can verify Hm plus 1 is equal to P inverse H. Alpha inverse is this. So by setting H is equal to Hm plus 1 and P is equal to H transpose, I can in fact rewrite my recursive equation in this very nice and simple form. The new estimate is equal to old estimate plus this is called K, gain matrix, that's a vector and that's a scalar. And how I can compute this K recursively, the K m plus 1 inverse is K m inverse plus this, which is equal to that. Therefore, if I want to update my m observation solution to m plus 1 observation solution, I already know this. So all I need to do is to be able to update Km plus 1. So if I update Km plus 1, I know everything of every rest of the thing. So this equation 16 is the final recursive form of the estimate. So I have built the recursive structure. Estimate based on m plus 1 samples, expressed as an estimate based on m samples. We have been developing the theory behind sequential estimation as opposed to batch estimation. We are going to update the estimate as and when a new data arrives. And we started illustrating the theory by sequential computation of averages. So in this case, H is a column matrix with all ones, and Z1, Z2, Zm are components of the vector Z. We have the average of m quantities, which is given by this. We calculated all the matrices involved in the previous theory. If you apply and specialize that to the sequential computation average, the equation for the sequential update of average, the least square estimate of the average based on m plus 1 observation is equal to the least square estimate of the average based on m observation plus the weighted sum of the difference between the actual observation, that the new observation that came to the table, minus the old estimate, So what does Zm plus 1 minus XLFS give? This gives you the new information, and that is also called innovation. What does it mean? I had the running average all the way up to m observation. The new m plus 1th observation comes into play. I would like to be able to find the difference between the new observation and the old. So you can think of the XLS as a prediction of the new observation. The observation comes into play. The difference between the new observation and the old estimate is called the innovation or the new information. I'm going to weight it by 1 over m plus 1. This can also be rewritten as equation 19. I'm combining the XLS. So it is the weighted sum of the average based on m information and the new observation m plus 1. So look at the weight. The sum of these two weights is equal to 1. Both the weights are positive. So now you know this is the convex combination of the two pieces of information. So if you think of it like this, if this is XL as m and this is z m plus 1, the difference is what is involved in 18. In 19, what is that I'm trying to do? I'm trying to multiply this by alpha, multiply this by 1 minus alpha, where alpha is equal to m over m plus 1. So the XLS m plus 1 is a point on the line segment joining XLM and ZM plus 1. This is the convex combination of the two pieces of information, the old one and the new one. As m goes to infinity, alpha goes to 1. 1 minus alpha goes to 0. So that means if you have been computing this average over a large number of observations, the new information does not bring about too much change in the average. The average tends to stabilize, and that's convergence. So this proves convergence of XLM as m, the number of observations, tend to infinity. So this is a very good example to illustrate the power of the sequential method. Now, there is another aspect of computation in basic statistics, sample variance. We all know how to compute the sample variance if you are given k number of observations. Now I'm going to rewrite the computation of the variance using the sequential method. Just like we were able to update the average or the mean sequentially, I should also be able to update the variance sequentially. So we are given a sample x1, x2, xk. In the previous slide, I assumed the observations are z1, z2, zk. Now here I'm assuming the observations are x1, x2, xk. Mu k is the sample average. The sample variance is given by this quantity, which you should all know from basic statistics. Please remember, I am dividing the sum by k to get the unbiased estimate of mu, the average. I am dividing this by k minus 1 to get an unbiased estimate of the sample variance. Biased, unbiased, these are statistical concepts which we will explore in much greater detail when we come to statistical estimation a little later. So when there is only one observation, there is nothing to compare. Variance comes in only when there are at least two people to be able to compare. Variance means the variation between the two. So S1 square is 0, so that's the boundary condition. So if I use this formula to be able to compute xk square, so xk square is equal to 1 over k times, this is the sample average. We now know how to update the sample average from the previous exercise. So let's assume I have computed the sample average of k plus 1 samples. So k times xk square, sk plus 1 square can be written by this summation. Now I'm going to use the simple mathematical trick. You can add and subtract. Mathematicians have exploited this kind of a trick to derive very many different interpretations of quantities. So I can add and subtract. I am going to consider this as one term, this is another term. This will be a plus b whole square. Now look at that. The second term looks at the difference between the old average and the new average. The first term describes the difference between xi and mu k, I running from 1 to k plus 1. So if I expand this using the standard formula for a plus b whole square, I have the first term, I have the second term, I have the third term. I have to rewrite this in a form that tells us that xk plus 1 square can be obtained from xk square and then some added quantity. That means I am going to simply increment the old estimate of the variance after the new observation arrive. So this is the basic idea. So now the rest of the derivation leads to simplifying this expression. So let's look at the first term. The first term can be expressed as, look at this now. This is the sum over k plus 1. Sum over k plus 1 is equal to sum over k plus the k plus 1 quantity. The sum over k plus 1 is essentially can be expressed as k minus 1 times sk square. Now look at that. This is the first term in the expansion in the previous case. I'm trying to express this in terms of the variance of the first k observation. We also know from the update of the sample variance xk plus 1 minus mu k. What is that? This is the difference between the new observation and the old average. That is equal to k plus 1 times mu k minus 1 minus mu k. Hence, xk plus 1 whole, this quantity now becomes k minus 1 times xk square. So if I substituted this in here, that becomes this quantity. That becomes this quantity. That becomes this quantity. So xk plus 1 mu, this term is essentially the term in here. You substitute this, you get this quantity, which is equation 24. Now I am going to consider the term 2 and 3. Please remember, we have expressed this as a sum of 3 terms. Yes, there is a little bit of an algebra. I am giving you all the expressions. Instead of trying to give you every one of the derivation, I am going to ask you to verify. I am showing the path. You simply need to be able to verify these things. Likewise, mu I minus mu k, this must be, mu k plus 1, sorry, this is equal to k minus 1 times mu k plus 1 whole square. So consider the third term. So this is the value of the second term. Consider the third term, which is the product term. The product term can be expressed as, look at this now, the summation is over I. This term is independent of I. So I can pull it out of the summation. So this quantity again can be written as x this way. Please understand, this quantity can be again written as this way. Why is that? This is sum up to k plus 1. Sum up to k plus 1 is equal to sum up to k plus the k plus 1 quantity. So the mu k plus 1, this constant term continues. If I simplify this, I get this term, which when further simplification gets you using 26. So this is mu k minus mu k plus 1, xk plus 1 minus mu k. Xk plus 1 minus mu k is the new information that is needed in computing the average sequentially. Therefore, the third term is now summary is k plus 1 mu k is given by this. So the entire third term using this is minus k plus 1 mu k minus mu k plus 1 whole square. So final assembly. So I have 3 parts. I'm going to substitute 24, 25, 28, and 21. So k times xk plus 1 square. After plugging in all the terms, I get this term, I get this term, I get this term. If I simplify this, I get this relation. Yes, there's some work involved in here, but in a lecture of this type, I want to be able to show you the pathway. Please remember that. Therefore, if I divide both sides and simplify, I get this relation. I get this relation, which is xk plus 1 whole square is equal to k minus 1 by k sk k plus 1 times that. K plus 1 times that. So now you can see this is the weighted average. So this is the weight, this is the weight, this is the old estimate, this is the difference between the square of the difference between the average using k plus 1 and k observations. Generally, you do everything in the batch mode. So this is the sequential version of computation of the variance. So if data is coming in, I would like to be able to compute the running average. I would like to be able to compute the running variance. So in sequential computations where data arrives in time, these are very useful formulas. In data science, we have two kinds of computation. One is sequential arrival of data. Another one is the batch mode where we have all the data available. So depending on the circumstance, we can compute the basic statistics, namely the mean and the variance recursive. With this, now I would like to be able to ask you to work on some exercises. Verify the correctness of the relation 16. Let's go back. 16 is a simplified expression. So I have given you all the expressions. I would like you to be able to verify the correctness of this expression. That's a very good exercise. Verify that the inverse of this is given by this. And what is that? That is essentially Sherman's formula, Sherman-Woodbury formula. So I would like you to verify this. What is that you need to do? You need to be able to take this. This is the inverse of that. So if you multiply these two quantities, you should get the identity matrix. So here the algebra involved is multiply P plus HH transpose with this formula to be able to see if you multiply these, that gets you the identity matrix. In which case you can verify that this is the inverse of that. Please understand, earlier case when I was dealing with matrices, we had Sherman's formula, we have Sherman-Woodbury's formula, we have Sherman-Woodbury-Morrison's formula, we have Sherman-Morrison-Woodbury's formula, 3 levels. I proved the general case of Sherman-Morrison-Woodbury's formula using partition matrices. Then we specialized it to Woodbury's formula and all the special cases. Now I want you to be able to explicitly multiply the two and verify. So this is an alternate way of trying to verify the Sherman's formula or Sherman-Morrison-Woodbury's special case. Sequential computation of sample variance, we already know this. Rewrite this in this particular form and verify that this expression is true. Again, this is simply an exercise in algebra. Please understand, you cannot avoid very good algebraic manipulations when you are trying to do mathematics at this level. So algebra should not bother you. You should be able to do these algebra very clearly and quickly. Exercises continue again. Please remember, I am not asking you to invent anything. I am giving you every little thing formula. Why? I want you to be able to verify the beauty of various ways of rewriting the expressions. So, which is the recurrence relation. So ultimately, what is the idea here? This is the recurrence relation for computing the variance, sigma k square. So you can talk about going from sigma k square to sigma k plus 1 square. Also, you can talk about sigma k minus 1 square to k square. Either way is fine. You can either take this step or you can either take this step. Both are sequential in nature. This module follows the development chapter T of LLD. LLD is Lewis-Lakshmivarahan and al. 2006, dynamic data assimilation. So with that, we come to the end of this module. So let me quickly summarize where we are. This whole sequence of modules that we talked about relates to modeling. So we talked about building regression model, linear model, nonlinear model. So what is a summary? The regression models can be divided into a regression model. The differentiation is it can be linear, it can be nonlinear. I'm now trying to summarize. It can be overdetermined, it can be underdetermined. It can be overdetermined, it can be underdetermined, it can be weighted, it can be unweighted. We talked about orthogonal projection, oblique projection, oblique projection. So now you can see linear, overdetermined, unweighted case relates to orthogonal projection. Linear, underdetermined, unweighted case, again, related to orthogonal projection. So you can see the multiplicity of ways in which we have covered this. And there is another classification is unconstrained, constrained. Optimization, where we talked about Lagrangian multiplier, we talked about penalty function method, we talked about method of regularization, we talked about strong versus weak constraint formulation, oh, this is a quick summary of all the things that we have done so far in the several modules that we have talked about. We may, if time permits, we may come back and add a few more ideas later, but I would like to be able to continue and move towards the computational problems arising from least square methods. This concludes the coverage of modeling in data science, your first look at modeling in data science. Thank you.